Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Carbon acidity, pKa of CH bonds, is determined by the stability of the conjugate base carbanion. Greater stabilization of the carbanion by electron withdrawing groups, EWGs, through resonance and or induction leads to stronger carbon acids, lower pKa. Moving on to the next step. Identify the acidic CH position in each compound. A. Norbornene 2,3 dione. The CH bonds are on the ring carbons adjacent to the two carbonyls, but the bridged bicyclic system and the alkene between the two carbonyls limits enolization. Moreover, there is no active methylene between two EWGs. B. Norbornenediene, similar bicyclic dietone. The CH alpha to both carbonyls is at C1, bridgehead, but in norbornene systems Brett's rule restricts enolization at bridgehead positions, making these extremely poor carbon acids despite having two flanking carbonyls. C. CH2, co-2-ate, 2-diethyl malonate. The methylene, CH2 is flanked by two ester groups, co-2-ate. The carbanion formed is stabilized by resonance with both ester carbonyl groups. pK 13. D. CH3 COCH to cook to H5, ethyl acetoacetate. The methylene, CH2 is flanked by one ketone, CH3CO, and one ester, cook to H5. The carbanion is stabilized by resonance delocalization into both the ketone carbonyl and the ester carbonyl. pK 11. Moving on to the next step. Compare C and D. In diethyl malonate, C, the carbanion is stabilized by two ester groups. Esters are moderate EWGs. In ethyl acetoacetate, D, the carbanion is stabilized by one ketone and one ester. A ketone carbonyl is a better electron-withdrawing resonance-stabilizing group than an ester carbonyl because the ester oxygen donates electron density back into the carbonyl, reducing its electrophilicity stabilization ability, whereas the ketone methyl group does not do this. Thus, the ketone provides stronger stabilization of the adjacent carbanion than the ester does. Therefore, ethyl acetoacetate, D, has a lower pKa, 11, compared to diethyl malonate, C, pKa 13, making D a stronger carbon acid. And for the final step, why A and B are weaker? Options A and B are cyclic diatones where the carbons alpha to both carbonyls are constrained in a bicyclic framework. Brett's rule prevents effective enolization at bridgehead positions, drastically reducing carbon acidity. Even for non-bridgehead alpha positions, the rigidity of the system does not provide the same stabilization as the freely rotating active methylene in C or D. Conclusion. Ethyl acetoacetate, D, has the most acidic methylene proton among the four options due to dual resonance stabilization by a ketone and an ester group, with the ketone being a stronger stabilizer than a second ester. Therefore, the correct answer is D. Therefore, the correct answer is option D.